Okay, hello everybody. My name is Jens Dittrich. This is Database Systems Lecture at Saarland University. And I figured, why not do a reaction video? There are so many reaction videos on YouTube. I've never seen a professor doing a reaction video to another professor's lecture. So that is what we will be doing today. So I skimmed around on the internet a little bit and thought which video we could take. And I'd like to take a video from a colleague from Carnegie Mellon University, Pavlo. He's a well-known figure in the database community, one of the few people that actually upload their stuff on YouTube regularly. He has many videos online, so go check it out. So Andy is very interesting, does crazy things here and there. And we will take a look at a specific topic called distributed query processing, which I believe fits well into the agenda we have in this course, database systems. So we already learned about query processing, query optimization on a single instance machine. And now we look a little bit into the distributed case with this video. So I will play the video, stop it here and there, make extra explanations. And I will pretend I never saw the video before. I've never seen it before, which is completely fake, of course. I saw it before and identified some interesting points in the video. So the video is 90 minutes and we only have 90 minutes. So we can't play all of Andy's video, but just parts of it. And I will map it to the stuff we had in this lecture before for you to make it easier to identify how he is explaining things and how am I explaining things and what is the mapping in between those two worlds. So Andy's sometimes does really crazy things. I don't know whether you've seen that. So I'll just I can show you. He actually did a video where he did a lecture from the bathtub. As you can see it below here, he did it from the bathtub. And I mean, come on, Andy, I can do the same thing, right? I'm actually also sitting in the bathtub, but you can hide it with a green screen. That's what I'm doing. You don't have to expose it to the entire world if you're sitting in the bathtub. And there are more crazy videos. Maybe I can play the most extreme thing he ever did later on. But for the moment, let's get some work done. So I will post a link to his video also then in the lecture material and below this video, which allows you to make the link. So let's start with this video. And that I start at 0. So that is how he enters the stage. The audio is broken, it seems, again. Sorry for that. Let's fix that briefly. Now it works.
Thank you. Did you have a good break?
Yeah, I mean, could have been better. Had to go to court.
Lawyers aren't cheap.
They are not.
Yeah.
Money's a little tight right now.
So whatever, the guy is a DJ, right? I mean, that's. I'm not aware of any professor who has a DJ as part of his lectures. Maybe I should also do that. Maybe I was thinking about getting a band like Stephen Colbert or Jan Böhmermann or something like that. Take that as a mental note. Organize a band. Yeah, with that said, we directly jump to position 337.
And send emails. Or he has problems. People send emails too.
Where he introduces, says a few things about OLAP.
So today we're going to be talking about OLAP systems, and we have this distinction between the OLTP systems where you're ingesting new information from the outside world, you're running transactions, you're updating your database, and then now with the analytical system, now we actually want to analyze all this data we collected from these OLTP systems and extrapolate new knowledge. And so this is not specific to distributed databases. What I'm about to describe here is not specific to distributed databases. I just want to show you, when you got in the real world, here's how you're probably going to come across these two different systems. And the OLAP system could be distributed, it could be a single node. The OLTP system could be single node or distributed. It doesn't matter. So you would have this bifurcated system where you have all your OLTP databases, and this is where people are going through the application, to the website, the phone app, whatever it is. they're making updates, they're looking at things, and they're hitting up.
So maybe just one clarification. OLTP means online transaction processing. So that's short-lived transactions, like you insert a new lecture into the database, a new student, a new professor, just a single record or a couple of records are inserted. You do a bank transfer from one account to another account. That's all part of what OLTP systems do. So OLTP systems are typically part of a bigger application stack. Somewhere underneath, in the middle of that stack, there's a database system that's called an OLTP, online transaction processing database. And on the other, on the right side, you see an analytical database. So that's used for analytical queries, a large group by statements that ingest a lot of data, that do analytics across multiple OLTP databases typically. And that's a very classical distinction to say there's OLTP databases and OLAP databases, because they require also for very different query optimization techniques. So in OLAP systems, you have to do way more sophisticated query optimization than you have to do in OLTP typically. OLTP is relatively simple to optimize.
These databases. But now what I want to do is I want to analyze and find some, run data science algorithms or whatever I want to run to extrapolate new knowledge on all these different databases. But I don't want to do it on the front end nodes themselves, because if I run a really expensive analytical query, that's going to take locks and slow down transactions and interfere with people using the application. So typically people want to separate these two. And so what you would have is a process called ETL, extract, transform, and load. There's a bunch of tools to do this kind of stuff. You might have heard of like Fivetran, Golden Gate from Oracle. Right? There's a bunch of tools that know how to take the data out of these OLTP systems, do some kind of cleanup, and then shove it into your backend data warehouse. And so the reason why you have to do this this cleanup process and the transform process, because oftentimes the schema or the naming of things in these different OLTP databases will be different from one database to the next. So the example I always like to use is Zynga, right? Zynga buys a lot of these different phone apps, and they usually leave the front-end database alone. But now if you want to run analytics across all your different, the different games you have, the data you collect from people, you've got to clean up the schema and make things be uniform, right? Because like one database might have, say a table of users. They might have the first name, the name of the column be F name, or first underscore name, or first name is by itself. Right, so
so he's alluding to multiple problems you have here in this world. So as I said, the OLTP databases are part of an application. They have to execute these short-lived transactions. So you don't want to put extra load on those systems. Load that is triggered by expensive analytical queries. So that's a very traditional approach to say, okay, we copy all the data from the OLTP systems into a different system that's dedicated and only runs those analytical queries. So that is done in this extract, transform, load process, which copies the data over from OLTP to the OLAP database systems, but also has to do the data integration part. So maybe fields are named differently, maybe the tables are named differently. So we have to do schema mapping the source schema, the OLTP's databases schema to the target schema. That's actually a very painful job that can be very, very time consuming. You can do tons of errors in that process. That's not that easy.
From a database system perspective, those are seen as different column names with different attributes. Because we humans, they know it's corresponding to the same thing. So you would clean this up in the transform phase, and so you put it into a standardized schema. All right. There's another style of that's becoming more common now. We'll see a little bit in a second. In a data lake, where instead of doing extract, transform, and load, you do extract ELT, extract, load, and transform. So you just dump all your files into a data lake, and then when you run your queries, you go ahead and clean things up and put it into the sort of a standardized schema. Right. So ETL is the classic way of doing this, but ELT is becoming more common now. But again, the main thing I want to just say is that you would have separate systems for these things. So now, we didn't really talk about what these OLAP databases are, the database itself is going to look like at a logical level. Right? We talked about it being a column store. We talked about it could be a shared disk system, a shared nothing system. We talked about how we execute parallel queries. But how you would actually model your data in an OLAP system is going to be slightly different. Or the preferred way of doing it is slightly different than how you do this in an OLTP system. And so I'm using the word OLAP, or decision support systems, or analytical systems or data science systems, they're all more or less mean the same thing, right? The idea is that like this is the repository. You're going to store all your data you've collected over the entire history of your application, and you want to find new things, right? So there's basically two approaches to doing this, or two different modeling approaches. There's a star schema and a snowflake schema. And everyone wonder why is Snowflake called Snowflake, right? Because they support Snowflake schemas, right? So let's go through the star schema first. This is this will be a sort of simplified form, and then Snowflake will be an expansion of it. So in an OLAP system, the way to sort of model them, a common approach to modeling them is this idea of a fact table and dimension tables. So remember before when I talked about schemas, I was like, oh, you could have, you would have a table for customers, and customers would have orders, and orders have order items, right? That's sort of like a tree structure, and that's very common in OLTP systems. But in analytical systems, oftentimes what you want to do is just do some analytics on a giant fact table, and then you do joins against these dimension tables to fill in supplemental information, right? So say in a really simple like Amazon warehouse, a data warehouse, you would have a fact table of all the sales that ever occurred in Amazon or Walmart, whatever it is, like every single item anyone's ever bought. So you think it's like billions and billions, maybe probably in trillions at this point. Like this giant table of just like a line, there's an entry, a tuple for every single item anybody's ever bought. And then instead of inlining in this fact table, instead of having like, here's the product name, here's the product price, and so forth, right? Or actually, you would have price. You wouldn't have the product name or like the location of the user and all these different things. You would store that as foreign keys to these dimension tables that sort of span out or emanate out from the fact table. Right, so you have a dimension table, you say here's the product category, sorry, product dimension table, here's the product category, here's its name, its description, here's the location of information where the person bought the item, the user is. Here's like a time dimension to say, instead of saying here's the exact timestamp or maybe when somebody bought something, I want to group it up by like per hour, per day.
Yeah, that's a very important schema that became popular in the 90s in those analytical systems and the OLAP systems where all the data was transformed into such a star schema. You find that in these decision support systems or online analytical systems, as they are called. And you will see it has some advantages, it has some problems. I will wait for what he tells about that and maybe add some more things.
Day, per week, per month, and so forth. And then same thing for additional information about the customer itself, right? So you have all these different foreign keys. So now when you want to run analytics and say find what are the top 10 items that people bought that live in this location at this time and are these conditions, you're basically scanning through the dimension table and joining with the dimensions, right? So you would go look up the product dimensions and do a join on that. And you would use the join algorithms that we've talked about so far, right? So this is the reason why this is a good idea, because the earlier OLAP systems, the early analytical systems, again, whether they were distributed or not, they weren't really good at doing, joining a lot of different tables, right? Like doing more than 5 joins, the query plans usually get pretty bad. So if you can simplify it, denormalize the tables down into a simple fact table and then in one outer ring dimension tables, you'll get better performance for your joins because the joins are more simplified. Yeah. So his question is, how does it simplify how does it simplify the schema? Are we merging this and making one? Yeah. So his question is like, you still have 5 tables here. Like think of like if I had, say the product one, right? I could have one for a table for category, and that would be a separate table. Another table for the product would be a separate category or separate table. Like you span out everything. You have like the multiple levels going out. You just condense it down so you have one level of dimensions going out. The alternative is what I was referring to now it would be the snowflake schema. You do exactly what I just said. You expand it out and have multiple.
Okay, so that's the major difference between the snowflake and the star schema. It's really that, as we have a sound problem here that's really nasty. It's an OBS bug again. Come on. You can barely hear when he's talking.
dimensions going out like this, right? You still have this giant
Then
fact
I have
table,
to
you
fix
still
the
have that thing you're
setup.
gonna
There's no way.
basically do a sequential scan.
So let's do an audio test. I play it and you tell me whether you can hear this. To my understanding, it must be pretty loud now.
The data that you're looking for, but now you're allowing for multiple levels of foreign keys coming out of this, right? So in the product table, again, instead of having the category information and the product information as a single denormalized table, it's now normalized and broken out. All right. Okay, so this seems kind of weird. Like this is it's a different way of thinking how to design a database, which we haven't really talked about how to do data modeling. That's done in Heinz College. But now we can build a database system that's optimized for ripping through a huge fact table and doing these joins quickly as possible.
Okay, so we had some audio problems. let's do it like this. Sorry, that's an OBS problem. It's really nasty. It keeps so it's the desktop, the audio from the video is connected directly actually to OBS, but it keeps disappearing every 15 seconds, and I have to switch it on again. It's very weird. I don't know. So. Yeah, so the major difference he just explained is really Snowflake and the dimension. Let's back up a little bit to what we had here. So the star schema is really the idea. You just have the central fact table with all the data, with all the transactional data condensed into that like sales records. And then you have dimension tables that allow you to select certain properties or specify how to aggregate the data, how to group the data. That's a trade-off because a star schema doesn't have to be fully normalized necessarily. Yeah, that's a performance trade-off. So the schema is designed in a way that the query optimizer can perform the joins relatively quickly. Yeah, that's a decision from the 90s when databases were still built on disks. Yeah, that's a trade-off they did basically at the time. And so you have redundancies in those tables. And a better approach is where we normalize our dimension tables is called a snowflake schema, and that is what's shown here, where you basically where's the video?
Through things really quickly. And this is why column storage is
Here it's showing it with a slide. Yeah? So you normalize it, and you have to do more joins in the Snowflake schema, but you have less redundancies and a better design. Yeah? So the Snowflake schemas are now more common these days. Okay. And there's a company called Snowflake, a famous database company. That's what he alluded to previously.
Going back here, if I'm trying to find all the items bought within a given location, then if I'm scanning this fact table, I only need to look at the location foreign keys and do that lookup. I don't care about these other columns, right? So there's a lot of optimizations that we can apply for this. All right, so here's the problem we're trying to handle today. We have an application server, we have a bunch of data. We want to run some join query. We want to join table R with table S, right? And let's say that both of these two tables are partitioned on some column. We don't know what it is at this point. And we need a way to produce this result, right? So the data is stored across these different partitions, but we need to produce a single result as if it was sitting on a single logical node, right? So the easiest thing we could do is just to take the data from the different partitions that are stored in different nodes and copy them or transfer them over the network to this one node, then do my join on RNS and produce the result. It'd work, it would be correct, but this is obviously stupid and defeats the whole point of having a distributed database, right? Because I'm not taking advantage of these additional resources. I mean, I'm showing them as a database drum, but it could be these additional CPUs over here, so maybe I could run the joins in parallel. I'm also assuming that the node up here has enough memory or even enough disk to store all these different partitions of data, right? So what we really need to be able to do is we need to be able to take a query that is trying to scan a lot of data, farm it out to a bunch of different nodes, have those run in parallel, and then coalesce the results and put things back together. And joins are the main thing we're going to worry about because we want to make sure that we don't have any false negatives. We don't want to be the case where there's some value in R that we try to join S, and there is a match that it does exist, but because we sent the portion of the query to the wrong node, we didn't send the data to the right location, we end up coming back with incorrect results. So we want to avoid that. So today we're going to talk about different execution models for distributed OLAP systems. We'll talk about how basically at a high level, how we're going to do query planning. Then we'll focus most of our time on doing distributed joins, because again, that's the most important thing we do. Spend most of our time in the system doing that. And then we'll finish up talking about cloud systems and data lakes and just sort of expose you to these different concepts and how people say data lake, it's not radically different, something brand new. It's just an application of distributed OLAP system technology or ideas.
So on the cloud part, we won't look that much today, except maybe the data lake part, but we will have a separate lecture here on elasticity and cloud systems and how to run a database system in the cloud later on. So not today.
Apply to a bunch of random files in S3. Okay? Okay. I'll say also too, just because we're running our data set in the cloud doesn't mean we don't care about all the things we talked about this semester. Right? We care about performance, we care about data correctness, integrity, strengths, and all those things. Like, just because you're in the cloud doesn't make things magically better, right? We still have to worry about all the same things, but now somebody else is running our hardware for us. All right, so the first design decision we have to make is whether we want to do a push or versus pull for the data. I think we talked about this before, but this matters a lot now for OLAP systems because we're reading a lot of data. So the first approach is to push the query to the data. And the idea is that we want to send the instructions of the task to execute some part of the query to the location where the data is actually being stored. Now, if it's a shared disk system, we can't always do that because like S3 doesn't expose raw CPU where you can run whatever task you want on that. So it may be the case we have to pull the data out to a compute node and then run some portion of the query there, but we don't want to have to do what I shared before, where copy all the data to a single node. Right? We want to break things up as much as possible. So the main goal here is the same thing we talked about before when we did query planning, is that we want to try to filter out and throw away as much useless data as possible before we start transferring the data. And so this is ideal if you can push the query to data because we can do as much processing as we can.
Yeah, so that's actually what we had, what we call predicate push down, or projection push down has the same effect. So you try to push the query as close to the data as possible, and that may even lead to pushing the data into the device. So I briefly mentioned smart disks or smart SSDs. Those are devices that allow you to already filter out, to perform simple subsets of the query language, like filtering. Yeah? So if you are able to filter out data already on the device, you have to send less data over the wire, whatever the wire is, whether it's a bus system, in a computer system, or whether it's a network, or whatever. So you want to, that's also called the data path. So on the data path, it is a path from the storage where the data resides on disk, SSD or whatever, to the computing unit, the CPU in this case. On that path, you want to process data as early as possible. Whenever it's possible to process the data already, you want to do that. And for filtering, for instance, the earliest possible way would be to do it on the SSD. You could even perform joins there if the SSD supported that. So that's the idea. And that's also called query shipping. You ship the query to the data as far as possible in order to avoid that the data has to be shipped to the query. That's the opposite, like data shipping. I think it makes sense to write it down here a little bit. So that is the slide he's using. So this approach one is called query shipping. That's a fixed term actually in query processing. And this is called data shipping. And those are the two options you have. You can also combine them in multiple ways, but those are the two extremes. And of course, the first thing is basically the general case for the special case we talked about, projection push down, predicate push down, and all of these things. So we will be talking about cases where you push down any part of the query, any subtree of the query expression, if you want. If you recall relational algebra, we ended up with all of these trees. And what you do in distributed query processing is you take a suitable subtree and push it down to a specific machine. Maybe another subtree is pushed down to another machine. That's called query shipping, versus when you ship the data, so he's calling it pulling data to the query, you ship the data from a node in a distributed scenario, from a server that sits somewhere, to that query processor. And that's typically way more expensive compared to just shipping the query. The query is just, that's peanuts, it's a few bytes. And if a server is able to execute the query locally, you always want to prefer that over shipping a large data set to another server where you then filter out 1% of the tuples and everything else gets thrown away. So that's stupid. That wouldn't make any sense. So it's a very important trade-off you see in distributed query processing setups. Yeah, let's continue.
To filter things out before we have to send it over the network to some other node or back to the client. The alternative is the reverse of this, is to pull data to the query, right? Again, this is, as I was saying, was like we have the data stored somewhere else, and we have to copy it to where we're going to run and compute the intermediate result, compute the result there, right? So an obvious way to think about this is, okay, I usually want to push the query to the data because the size of the query itself is going to be small relative to the amount of data I have to access or send around. Right? Most SQL queries, maybe a couple tens of hundreds of kilobytes. The largest, like the actual SQL string itself, the largest SQL string I know about, I've ever seen is from Google. They told me they had one query itself was 10 megabytes, right? It's like a dashboard. You click a bunch of stuff, and then these giant in clauses, right? That's not the entire story though, because again, if you don't have a way to run any code or run that query, then you can't push the query to the data. And so the lines get actually kind of blurred in the cloud because some of the cloud vendors for their distributed cloud storage, object storage, will actually let you push the query to the data in a limited fashion. Then it does some local filtering, and then you pull it to the node where you actually want to run it and do further processing on it. So in Amazon S3,
I think I don't have to look at these concrete product things here, because the technique is always the same. It's a very old technique, this trade-off. So let's jump forward to the example he has in mind. So he always has an application server that wants to perform a join, and you have two nodes in a distributed database systems that keep some of the data.
My query shows up, I want to do this join. I partition P1 and P2 on two different nodes, I partition RNS on two different nodes. So I would send the query to the first node. The first node says, I know I need to do a join on RNS, but I don't have all the data. So let me push down a plan fragment down to this node and say, hey, by the way, do join on RNS for these IDs that I know you have. And then this sends back the result. Right? It ran the computation locally, sends back the result. The first node is responsible for combining the results and then sending it back to the client. Right, and we can do this because again we have compute memory here in a shared nothing system, so we can access our local disk and do this processing. Yes.
Yeah, we'll jump again a little bit. He explains it later on. Again, a bit more clear. I will jump to this point in the video. Because now we will look at different scenarios how a join can actually be computed in such a world, and it's better in the following.
Before, maybe we just cared about how many blocks I got to rewrite in the disk when I'm doing a join, but now I got to be aware of where the data is located and where the result's going to go or where it's going to come from, and I account for that in my costs. So, again, I said query optimization, query planning is hard. Distributed query planning is even harder. And again, there's no magic bullet to make this work.
Yeah, that's true. It's more complex because even on the same layer in the storage hierarchy, you may have different costs. You remember we talked about the NUMA architecture. We have different main memory regions, and CPU is attached to a specific main memory region, and accessing that local memory region is slightly cheaper than accessing a remote memory region. Now we have similar effects here across all the layers in the storage hierarchy. We have to factor in the costs for shipping data over to a different server. for instance. That could be part of cost-based optimization, of course. If you extend your cost models to factor in those costs, you can enumerate even more planned alternatives in such a distributed scenario with a query optimizer that understands the distributed scenario. So it makes it only harder. Things won't get easier by factoring in a distribution.
All right. So there'll be some systems like DB2 where they're actually, when the system boots up, they'll run some quick micro benchmarks to see what's the latency between different nodes, and they can use that in their calculations for query costs. All right, so I showed before also too that there's one node sending a request down to another node, and I said it was a planned fragment, but I didn't really define what that actually physically looks like, right? So there's two approaches to send out planned fragments to different nodes in a distributed system. The first is we can send the physical operators, like we showed before when we talked about pipelines, where I could break up the query plan into successive physical operators and send that down, and then now the other system then just takes the query plan and executes it as defined on the data that it has local, right? And this is what most systems do, right? SQL query shows up once, you parse it, plan it, generate a bunch of query plan operators, break them up and assign them to different physical nodes, and then send those out. An alternative is to take the SQL query on the node where the query shows up, parse it, plan it, generate physical operators, then convert it back into SQL again, but for the different nodes that are going to be in that are going to execute the query. And the idea here is that if you do all your parsing at a single location, or you're planning at a single location, the decisions will be made, the optimizer decision will be made on whatever statistics that they have collected at that node, which may not be accurate representation of what's at the different nodes. So instead, if I can convert my sort of plan fragment back into SQL, send that over to the node that's going to actually run that plan fragment, it can then run its own optimizer with its own locally collected statistics and potentially make better decisions because it has a local view of the data of how it actually wants to produce the result.
You could actually do a third approach here that is send over logical operators. You don't have to go back to SQL. You could also, if there's a central instance that receives the entire query, breaks it up into fragments, and the logical fragments could be sent over to the distributed nodes and then further be optimized. He does the extreme approach. He goes back to SQL. So you break the big query into, we will show an example, we will see an example in a moment, into SQL again. And then he has another advantage because you could, in theory, use different types of databases, different types of SQL processors on each of the nodes. Yeah? If they understand SQL, it's fine. Typically, the systems don't directly understand the logical algebra, logical operators. So sending over logical operators would typically only work within the same system, within the same product, so to say. But if you send over SQL, you could actually use different database systems at different nodes, and it would still work. So that's a more flexible approach, obviously.
Right, so maybe the case that for this second approach, I send the different SQL plan fragments to the different nodes, and one node says, my data looks like this, I want to use a sort merge join. Another node says, my data looks like this, I want to do a hash join. At the end of the day, it doesn't matter, right? Because as long as I get the correct results in the join when I combine things, but each node can make its own local decisions about things. So the only two systems I know that do this is Single Store and the test. Single Store is a distributed, now it used to be in memory, it used to be memSQL, but now it's a distributed real-time analytical system. And when they send the SQL query, they actually annotate it with non-standard SQL constructs to say things like, hey, run this SQL query, and by the way, send the result to this other node here, sending back to a single location. So you can actually put hints into the SQL plan, or the SQL statement itself, to tell the local node where to send things. And then the test is it's a middleware system that does distributed MySQL that came out of YouTube. What's that? Surprised by this? YouTube's huge, right? It runs MySQL. It's a weird reaction. Why wouldn't they? Why would you make it sound like they wouldn't have a big database? Okay, all right. Yeah, so anyway, so it's been spun out as PlanetScale, which is a new startup. But again, same thing. They have the SQL query shows up. They generate the query plan, and then for distributed query plan, and then they convert it back to SQL because the different nodes in the cluster are just running bare bones or stock MySQL. So they can't accept query plans. They have to set, they have to run their own SQL statements. They have to take in SQL and run those. So the basic idea is this, right? So say if you're doing where you're sending SQL queries. So this is my original join. This arrives at the planner node, but then my data is broken up into different partitions. So I would generate what the physical query plan, distributed query plan that I want to run for this join. Then I'm going to reverse it back into SQL, and then send down each node, a version of the query that is targets the data that they have. Right.
So here the node on the right has all the IDs from 201, including 201, including up to 300. So basically, he does a horizontal partitioning on r.id and SID. So co-partitioning, as we called it in this lecture, and then along those co-partitions, he sends down the different queries. So basically, he creates a separate query for each of those partitions.
And each node can then parse it, plan it, optimize it just like before, as if it was a single node query. And then they send back the results to a single location. And then there's some coordinator node that has to union all the results together.
Yeah, this coordinator thing, so it's sometimes depicted as a separate entity, a separate server, but you could also run the coordinator on one of these nodes, one of these database nodes. That would, of course, put extra load on those servers. You could also do it round-robin style. There are many approaches how you could do that. But here he is assuming a separate coordinator receiving the query and sending it to these database nodes.
Okay. I would say also, too, the advantage of this is that you don't need to have super accurate statistics at like the centralized coordinator node, right? Because again, these guys, each node's going to analyze on the data that it's responsible for, and therefore it can make the best decisions about how to do query optimization. Okay, so obviously the joins are the most important thing we want to do in an OLAP system, and the efficiency of the joins is going to heavily depend on what the query actually wants to do and what how the data is actually partitioned, right? And as I showed in the beginning, the easiest way to do a join is to put all the data from your different nodes back into a single node and run that.
Here's another analogy that comes to my mind. Yeah, so when is a join efficient? Think about the simple hash join. If you already have a hash table on the join key of one of the relations, then it's super efficient because you don't have to, or even more efficient, because you don't have to build the hash table in order to be able to run the join. The same is for the sort merge join. Yeah, it's super efficient if both relations are already sorted on the join key. Then you completely avoid the sorting step. And here, it's a very similar observation. This join is efficient, the distributed join is efficient if the data was already partitioned ahead of time. Of course, when the query comes in, you can still repartition all of your data, your terabytes and petabytes of data if you want, but that will be costly and will take a lot of time. So it's better to anticipate that queries like that come in and do all of this, be it an index, be it sorting, be it partitioning ahead of time to be able to answer the query faster once it comes in. That's always the same idea here. This is also called physical design in databases. So physical design means, so when you think about physical data independence, when we teach the relational model, relational algebra, we always hammer it in your heads to say, we don't care about the physical layout of the data, we don't care about the machines, hardware, whatever. That's not our concern because that's done later. But in order to make a system efficient, eventually you have to make decisions on how to organize the data physically. Creating indexes, sorting the data, putting it on device X, putting it on device Y, putting it on this server or the other server. And all of that process is called physical design.
That's not realistic. You can't, it won't scale. So we need a better way to do this. So there's going to be 4 different scenarios we have to deal with to do a distributed join. And the basic idea is that we want to say just join two tables R and S, and we need to make sure that the right tuples from R and the right tuples from S are at the same location, at the same node, so that when we do a local join using any of the join algorithms that we talked about before, it usually will be hash join, but it doesn't necessarily matter. But when we do the local join at the node, we're guaranteed that the data from R that could potentially match to the data in S are located at the same node. Because otherwise, if like ID equals 1 for R is at this node, and ID equals 1 is at another node for S, then when I do the join, you're going to get false negatives. Right? So we want to avoid that. So again, once we get the data at the right node, again, ideally when we keep this distributed, we can then run a local join algorithm, produce the results, and then send it back to some location to coalesce things. So we're going to go through 4 scenarios from best to worst case scenario. And the technique will be roughly the same or actually will be the same whether it's a shared disk or shared nothing system. Right? In the case of shared disk, it's just where do you send from the shared disk to what compute node. For a shared nothing system, assume the compute node already has the data local, but it may need to send it out some other location. All right, so like I said before, best case scenario to worst case scenario. Best case scenario is that one of the tables that we want to join is replicated at every single node in the cluster, right? So going back to the dimension tables I showed in the beginning, say there was a dimension table on zip code. There's 40,000 zip codes in the US. That table is super small. It's only updated by the post office 4 times a year. So I could easily replicate that on every single node. So then now when I do my join, all the data I need from one of the tables is right there. And I don't need to communicate between the different nodes to send data around. Right? So R is partitioned on ID, and I have 1 to 100 and 1 to 1 to 200, and then S is replicated. So that just means, again, there's a complete copy of the table S on every single node. So to do the join, each node does the join locally on R and S, and then we need to coalesce the results. So say this node here will transfer its results to this other node, again, just union them together, and then produces the final result, correct result. Again, if it's shared nothing, assume they have a local copy. If it's shared disk, then every node is going to pull S up into its local memory, or local disk. All right, next case scenario is when the tables are partitioned.
So I think here it's a bit confusing because there's a bug in the slides. He fixes it later on. Yeah, so I think it's this slide. So the range should be from 101 to 250 for the second relation as well. Yeah. That's important here. Yeah, so here down there, the S starts at 101 again. Otherwise, this doesn't work.
On the join key, and the partition ranges overlap. Right. So in this case here, R is partition ID, S is partition ID, and then although the ranges aren't the same, if we make R the outer table, it will cover everything in S. And because I'm doing an inner join and not like an outer join, I don't care that I don't have a match from 101 and above in R, because I only care about does R match into something in the S. Right? So again, there's no data transfer. Every node has all the data that they need. I do my local join, send the result from one node to the other, coalesce them together, and I'm done.
So this works if you have complete co-partitions, as we had them in the lecture before. So generalized co-group join. So if you do a join between R and S, and from R you have all the IDs between 1 and 100. Here you even have more IDs from S. It wouldn't be necessary. From 1 to 100 would be enough. And on the right side you have from 100, in R you have the IDs from 101 to whatever, and in S should also be at least 101 to whatever, covering that range of R. Then you can compute the result to this co-partition here. So whatever you have on SIDs here that don't find match partners here, doesn't matter. Yeah, it really doesn't matter. The result is complete. Yeah, if this would be partial, like in this scenario, S only has the IDs from 151, you wouldn't find matches with R in the range from 101 to 150. So that wouldn't be correct. And he's correcting it later on the slide. So that would be the standard co-partitioned joint, or in the standard database literature, it's also called a Gray's hash join. Gray's hash join alludes to Jim Gray, famous figure in the database community. But the general case is a generalized co-group joint, as explained in my lecture.
Right. So there's no intermediate transfer between these two nodes.
Okay, so we can jump directly to the next scenario here. That is
From 1 to 100 on the first node, I'm guaranteed if there's a tuple that exists, I will see it in S. Okay.
This next scenario is scenario 3, right?
So the next scenario is when the tables are partitioned on different keys, right? And so what we're going to do is we're trying to figure out which table is the smallest between R and S, with the inner table and the outer table. And for the smaller table, we're going to send that out, a copy of it or the portion of the data that I have at my node to all other nodes in the cluster. So this is called a broadcast join. This is typically used for hash joins. So if you ever see something called a broadcast hash join, or if somebody says broadcast join, it's usually a hash join that's doing broadcasting. So in this case here, R is partitioned on ID, and that's what we want to do a join of that. But S is partitioned on value, right? So we can't do the join because we don't know whether from SID 1, is that going to be on this node or the other node, right? And we would have a false negative. So in this case here, because S is the smaller one, we're going to send a copy that I have from this node to this node, and then likewise, he's going to send me his copy. And then now I'm back where I was at the beginning, where I had S was replicating every single node. All right? And I do my local join. Every node produces this.
Yeah, just again, to clarify, maybe pulling up the slide. Here, scenario 3. Yeah. So problem being that, that's a major difference here. You partitioned on the same ID, co-partitioned partially here with overlap on that ID. Sorry, I have to. Right, and now you're changing that. So only R is partitioned on ID. So all the tuples with an ID between 1 and 100 are on this node, 101 to 200 are on this node. And now S is partitioned on attribute value. And you don't know the relationship of ID and value. There could be a functional dependency, correlation could be, but we don't know. So we have to make sure that all the tuples that have a S.ID in the range of 1 to 100 are available on this node. So part of those tuples will be here in this partition, and part of that will be there. So you basically repartition the partition. So whatever the data you have available here in this S-val partition with values in the range from 1 to 50, you now partition it on attribute ID. And the IDs that are in this range stay on this node, and the IDs that are in range 101 to 200 are sent over to the other node. And vice versa. You do it with here that's the second slide, you do it then with this partition. You also have to repartition that one, and such that the tuples from S that have an ID in 1 to 100 are received here. And then you can do the join. Then you're basically in a co-partitioning scenario again. Then you have the perfect co-partitions on each node, and you can again join those co-partitions independently, and then you're done. Yeah, so that's basically what he's explaining here, just using terms of our lecture.
It's the local result. First guy sends it to the second guy. I coalesce it. Right? So we had to transfer data, but we only had to transfer data for S and not R. Yes. The question is, what is the objective of partitioning by value? Like, why would I want to partition by value? Maybe there's like 1,000 other queries that also do lookups on value, right? But this one query shows up and it wants to join an ID, right? So her question is a sort of larger question that we've sort of talked about this semester of like, okay, great, the relational model has this nice abstraction where you don't really care how data is actually being stored or where it's stored. But then that means that someone's got to figure out what indexes to build, how do I partition my indexes, or how to partition my tables. So it's an NP hard problem to figure out for a given set of queries, what's the optimal partitioning key for my table. And as I said before, even though it's optimal for most of the queries, it may be the worst thing to do for a bunch of other queries, and you still have to be able to support them. So in this case here, someone decided let's partition this table S on value, but the query shows up and it wants to do a join on ID. So again,
yeah, that's the risk in these kind of examples, yeah? Because maybe you don't know the full workload. You don't know which other queries are received. Maybe the partitioning scheme you're coming up with, and you're deciding to partition your data like that, based on whatever query you have in mind. But later on, other queries come in that actually suffer from that partitioning. Yeah? So you have to make decisions. What kind of physical design will you do in a database such that all of the queries benefit, or the sum over all queries, the execution time over all queries that you receive is minimized or something like that? That's a difficult problem.
The database system has to figure out where the data is actually located and compute the result. There are some tools that try to figure out the optimal partitioning key for you, but again, it's not guaranteed to be the most optimal thing for all possible queries. Okay. So the last scenario is, the worst case scenario, is when both tables are not partitioned on the join key, and so I need to basically reorganize, or shuffle, as it's called, a shuffle join, to send out the data across all the different nodes so that we can then compute the join locally like we want. So in this case here, R is partitioned on the name field or name attribute, S is partitioned on value. I want to join on the ID field, so I can't do I can't do a local join yet. So I basically have to do a reshuffle, a repartitioning, so that I basically do a local scan, sequential scan on the data at each node, then partition it by ID, send out those buffers, send out the results, or the intermediate results to the different nodes. All right, so R will go over here. This copy of R ID within that range goes there. The R values within this range go here. And I have to do the same thing for S. And then now I'm where I was before, where now I have the data for R and S at each node matches up to my partition range.
Yeah, so as you see from these scenarios, the goal is always to end up with co-partitions. And what changes over the different scenarios is when do you do the partitioning? Do you do it before the query comes in, or do you do it after you have received the query and then feel like, oh, you have to repartition the data? Yeah, and of course, it's always better to partition in advance. Of course, you could also do it like that. You keep the partitions for the next query. Yes, once you did the partitioning, maybe another query comes in later on that could benefit from those partitions. Yeah? That would be another way of doing that. Yeah? So you don't have to. So whatever temporary data, and those partitions could be considered temporary data, created during query processing, whatever you create in that process, you could keep it. Why not? Maybe you can benefit from that, and then you don't have to repartition it again. If you get 10 times the same query on the same join condition, maybe you only repartition it once, and then all the other queries benefit from that. But in the end, you always do a generalized co-group join.
I compute the local join, and then send the result over. Right? Yes.
I think we can skim over that and go to the next scenario. That is an optimization technique that's important. That's called SemiJoin or SemiJoin reducer.
Okay. So there's one optimization we can do for this in some scenarios called a SemiJoin. And the idea here is that it's almost like vertical partitioning or projection pushdown, where instead of having to send the complete copy of a table from one node to the next, as I'm doing my join, I I can send just maybe the portion of the data that I actually need to compute the join, and then the result I get back doesn't need to be the complete materialized tuple. It's just the IDs, the primary keys, or the IDs that actually did match for the join. So let's say I'm doing a join like this, where I join R and S on ID, and my output of the query just needs to be the RID. I don't actually care what the values is, what value I have in SID. I just need to know that there is a match, right? And so if without a semi-join, the way I would have to compute this is that I have to send all of S to this node and then all R to this node to compute the join and so forth. Right? But now you're actually setting up the entire materialized tuple. But instead, with a semi-join, I really only care about is there a match at the other node for my outer table, for something in R. So it's essentially this query, right? Select RID from R where there exists some tuple in S.
Let me switch to the slides because this video is on top of that slide. I think here we go. Yeah. So he wants to have all the IDs of tuples from R that participate in a join of R and S. So in other words, and that's how the semi-join is defined, is to say, give me all of these RIDs, and actually distinct RIDs, that participate in a join with S. So maybe you remember we had it in relational algebra in the undergrad lecture. So a join, typically when you have a join between two tables, you create a new schema. You have some attributes from relation R, some attributes from relation S, and as a join is basically just a subset of the cross product anyway. So typically you create a new schema. You don't have to, but typically you do. And the semi-join doesn't do that. The semi-join is more, and that's where the semi, why it is called semi. It's not creating a new schema. It keeps the schema of one of the relations and selects tuples from that relations. And semantically, the question being answered by semi-join is, which tuples would participate in a join with the other relation? So the question he's answering here with a semi-join is, which tuples from R would participate in a join with S? Yeah, and the result of that can only be a subset of R, yeah, or subset equal R, of course. Yeah. So it feels more like a selection. You're selecting tuples that would be part in the join with S. That's a semi-join.
S, the one that says you need one, it's basically true, is this match, if there's a join. So now when I want to do the join to this other node here, I just send the RID column to this node. It does that join, which is basically matching this, and then I only send back the RIDs that match, not the entire tuple. So in SQL, there is not a semi-join. You can't, like, same way you can declare an inner join versus an outer join. In most systems, almost all systems, you cannot declare that you want a semi-join, and Pavlo does support this. There's another system that does, there's something from Microsoft that does this too. But underneath the covers, the query optimizer can figure this out and say, oh, I know you don't care about actually the result of the values from the inner table. So they'll have a semi-join implementation that they can then use to minimize the amount of data transfer going from one node to the next. All right, so this is a very common optimization that you would have in an OLAP system, because again, the network transfer is usually the most expensive thing. Yeah,
maybe let's go through that example in more detail. I'm not sure whether it was clear from Anja's explanation here. So semi-join, first thing what he explained is he expressed it through this exists subquery. That's one way of doing that. The other could be so any join where you just select attributes from one of the relations and then write a distinct in front of that. Yeah, it's the same thing. It's also a semi-join. That would also be okay. But back to the example, he's basically trying to explain. So in this situation, we have two relations R and S, and this relation sits on server 1, and this relation sits on server 2. Yeah. Another question is, okay, how do you perform a join? No. And here the idea is not to partition the data, but to minimize the data transfer. And you could do that by trying to figure out which tuples would take place or participate in a join of R and S anyway. So typically you do a join, but not all tuples participate. And how that and the idea of the SemiJoin or SemiJoin reducer, as it is sometimes called, is to say, okay, basically I could first send over all of the distinct IDs of one of the relations to the other side. I'm explaining it now for one direction, but you could also do it for the other direction. So let's assume what I do is I do a projection of R on column ID. And I do that in the relational algebra sense, saying, okay, I only want to have each ID once. So it's a distinct set of IDs of R. Then I send that over to the other server. And here, on that other server, I actually perform the join with that column I receive. So I only receive this here, only, oops, what's going on? Oops. Where's my pen? My pen doesn't write anymore. Why doesn't this write anymore? Sorry. Interesting. Not the first problem today. Here we go. Okay, so this part basically creates a set, or in a database lingo, a column of distinct IDs. So I send it over, and then here I do that join. So basically this will be joined with S. Okay, so this would select the tuples from S that take part in the join with R. And this is actually run as a SemiJoin. So basically, where is this rubber thing? Here, right? So let's do it like this. Yeah, this is a symbol for a SemiJoin. So it's like a join symbol. Maybe let's give it another try. So it's like the half-open join symbol. So you want to select all of those tuples from S that take part in a join with R. So for R, you know the IDs, so you don't have to ship all of R to this server to perform that. So this condition will select all the tuples from S that take part in a join with R. So by that, you hopefully get a subset of S and not the entire S relation. Yeah, so this gives you a subset of S, and that subset is then shipped again to the other side, to server 1. So let's call that subset, whatever, S prime, subset of S. So you ship S prime to the other side, and then you do the actual join of R with S prime. So the goal of all of that is to reduce the amount of data that you send over, by first sending just the IDs from one of the relations to the other side. With that, you can determine here in this box which of the tuples from S actually take part in the join. Yeah, then you only send over those tuples S prime. Yeah, that is a set of tuples that take part in the join with R. Send them over. Yeah, and then you do the actual join, and the result of that is the same as shipping all of S to server 1 in the first place and then joining it. Yeah? Just you ship less data. It doesn't have to reduce the size of S, but depending on statistics and selection conditions, it can make a difference. Yeah, right. That's what I want to show here.
If it's in the same data center or the same rack, maybe less of an issue. But certainly, if you're going across the wide area network, it's going to be slow. And so the SemiJoin optimization is the way to go. Okay. So I want to finish up now talking about cloud systems. And again, this is just sort of expose you to a bunch of...
Okay, so as I said, so we'll jump over a few things and I will directly go and where he explains data lakes. It's a more recent term. I don't know, it was invented maybe 6-7 years ago. And it's interesting to know about some things about that. So basically, yeah, let him explain.
So the next common trend we see is for OLAP systems, it's called data lakes. Basically, it just means that there's some kind of centralized repository at your company, your startup, your organization, whatever it is, that people can dump in all sorts of different types of data, like structured data, the things that have been parsed, semi-structured, maybe like log files or something, and unstructured data, like binaries, images, video. You dump these all into a centralized repository without having to define a schema ahead of time, or ingest them into the database system, convert them to the data system's internal format, and then I can come along and run queries on top of these files, and as if it was a full data warehouse that has ingested things. So, say that again, without a data lake, the kind of system we talked about so far in a data warehouse, OLAP system would look like this. Before I can put any data into the database, I got to call create table. This goes to the compute layer. It's going to update the catalog and say, okay, now I know about table foo. That's these columns or these types, and it'll figure out where it's actually going to store them on files or disk in the storage layer. And once I've done that, now I can call insert. The node's going to look up in the catalog and say, okay, I want to insert to foo. What do the columns look like? Where does it actually be stored? And then I can instruct the node where to actually write things. Right? The same thing for select. I go to the catalog, and now I can use scan all these guys. So in a data lake, the sort of structured storage layer goes away. Like even though it's S3 and S3, it's just writing out blobs. The data system itself is responsible for what the binary format of what's putting into those blobs, and that would be structured as defined by the schema. But the idea with now a data lake is that I have these S3 buckets. It's got a bunch of CSV files, JSON files, Parquet files, column store files, whatever.
So just one footnote to that. Data lake, or what he depicts underneath for the moment, you could also call it a large file system. Yeah? It's a bunch of files, you get the data. So there's a huge difference to what he explained with databases. Yeah, putting data into a database system is really a painful process, because first you have to create this appropriate schemas. Then whatever your data format is of the input data, CSV files, Excel files, or whatever, you have to bring it into the right schema that you just created for the database. Then there may be errors in your input data. Yeah? That may be a problem. The database system won't allow you to insert those errors into the database system. So that's a very painful process, or can be very painful to upload your data into a database system. So that's one extreme. A database system is one extreme. It's also called schema first. You first design the schema, and then you can only insert data that adheres, that matches that schema. In contrast, in a data lake, it's the other extreme. You can upload whatever you want. That's also called schema later. But then when a query comes in, then you have to do all of these. You have to match the data. If you have the data in different formats, then at query time, you have to be able to resolve those mismatches and match the data. So both approaches have pros and cons. Data lakes, of course, have the approach that you can upload anything without thinking too much about it. And in contrast to a distributed file system, a data lake also has some sort of catalog. So catalog meaning a small kind of search engine style list of the files that are available on the data lake. And for each file, you have a description. Okay, that's a format. That's in maybe those are the attributes. If there's a schema, that is a schema. Those are the fields. That's kind of a short description of the data of each file. This facilitates matching the data when the query comes in.
And now when my select query shows up, this node's still got to figure out somewhere from a catalog and say, okay, you want table foo, it's located in these files and these S3 buckets or these blob locations, right? Maybe there's some information about what the schema is. Maybe there isn't, right? But I go to this catalog service and say, where's the data I want? and then we know how to go to the data lake and get it. Yes?
Data lake allows like semi-structured or maybe unstructured data. Does that mean there are no buffer in it?
This question is, if the data lake allows for unstructured and semi-structured data, does that mean it's no longer in a data format? Yes. Or table format? Yes.
So it's no longer like, so it's basically kind of like,
So the question, is it like MongoDB? No. So think of like even worse. Like think of like it's a directory in your local file on your local laptop.
just like Google Drive.
It's like a Google Drive, like Dropbox, whatever the kids are using these days. Yes.
Like how would they interpret, like how would you even translate like a SQL query into that?
Right. So the question is, how do you actually translate a SQL query into something that can hit up unstructured data, right? So you would potentially have to have either functions built in that can know how to, like, the data set may have to know how to parse CSVs, parse JSON, right? And you would have to say, okay, if I'm looking for this column or this table in some of these JSON files, if the JSON document, each document is missing that attribute, then I ignore it, right? But if it's a bunch of random binary images, you would ignore that, right? So this catalog thing, I'm being vague. There's a catalog service that says, okay, you want this table foo? It's defined by these files in your data lake. There may be a bunch of other files that are like images or whatever, and it just knows to ignore them.
Would it consider like this kind of system you just throw like a key value storage and then just go back to whatever binary data is?
So your question statement is, instead of having this data lake approach, what if you had a key value store where you just, for given key, you throw back data?
Like literally the only API that the new warehouse provides is like the perfect example.
That's S3 or Azure Blob.
Yeah, so this discussion, to recap, someone was asking for MongoDB. What is MongoDB? MongoDB is a key document store. So basically, it provides a mapping from an arbitrary key to a document. A document typically being some JSON document, but it could be anything. So it's basically what an index would be doing, a key value mapping, where the key is anything and the value is a JSON document. So that's not the same thing as a data lake. It's related in that it is very unstructured. Data lake is really more like a file system plus a catalog. Yeah? And as the student then asked correctly, okay, what do you do if the query comes in? Yeah, then you have to provide all of those mappings. Assume you have whatever 5 CSV files, all in different formats, and now a query comes in, as maybe a SQL style query that wants to select the correct data, and then you have to map that query to all of those 5 different files in different formats once the query comes in, and that may be super, super hard and terrible to do. So actually we built a system like that 20 years ago at ETH. At the time, data lakes were still called data spaces, and data space management system. And we had all of those problems. So it's a really terrible thing to do if you want to have a structured query like SQL that you want to execute on unstructured data. It's a nightmare. It's an extreme I can highly recommend against. Yeah. So and that's the reason why on these unstructured data collections, typically you use more like search engine style services, yeah, or lightweight integration mechanisms. But if you want to do a more structured query, if you want to support something like that, you first have to invest something into your data. Investing means creating a schema, integrating the data, yeah, bringing the data into that unified schema, and then everything is so much easier. Yeah? So you have to do this upfront investment. And you can do everything in the middle. So there's one extreme, the perfect optimal database schema, which you will never get to, whereas it's a data lake without schema whatsoever. The truth is somehow in the middle. Yeah, but any of those extremes typically is very, very expensive, either for the upfront investment in a database system or at query time, because it gets super hard to query that mess of data.
But again, someone needs to understand the contents of what's inside them, right? So a bunch of these logos you guys are probably familiar with: Snowflake, Databricks, Google BigQuery, Amazon. Trino is a fork of Presto, which came out of Facebook. Again, I screwed this up. There's PrestoDB and PrestoSQL. They don't like each other because Facebook owns one, not the other. And then, so the guys that on Facebook, they made Trino, but they're basically the same thing. Which one's better? It's unclear. And then Hive also came out of Facebook. Hive was doing SQL queries into MapReduce, which is a terrible idea. Facebook realized that, and then they built Presto. But anyway, so like to its point, like someone's got to figure out what's actually.
If you ever heard about MapReduce, we also did research on that, I don't know, 12, 13 years ago. It was a very hype topic at the time to process really large data sets on large clusters. No one would ever do that anymore these days. It was an invention done by Google. You can do it much better than that, and that's why saying it's a terrible idea. You shouldn't do that. Hive was a database system built on top of MapReduce. Yeah, you shouldn't do that.
These files and these different these OLAP systems know how to have. They have engines that can parse, like Parquet, parse these different data files, and then run the SQL query on it as if it was, if it was the system's internal format. The question is why is it a terrible idea to build SQL on top of MapReduce? We'll just save that for next week. Yes. Okay.
Yeah, okay, we don't have that in the, okay. Actually, we wrote papers on that. MapReduce is not flexible enough. You don't want to do that. MapReduce is too slow for that. It's inflexible. You can play many tricks with that, but there's so many more better approaches. So basically, it always boils down to translating SQL into some sort of physical operators in the physical execution plan. Very flexible physical execution plans that are then executed. That's state of the art. That's way to go. No matter which system you build, you will end up doing like something like that.
Yes. So his question is, what's the advantage of storing the raw data and then processing it on the node rather than pre-processing it once and then reusing it? So that's the ETL versus ELT thing I said before. So like you could like take unstructured data like log files like from a web server, parse that into like the date field and so forth, right? You could do that and write out more files, but that assumes that the whatever the query is going to want that data sort of processed that certain way. So the argument for the data lake is just put all your data here, and then everybody who wants to then consume this data can write their own transformation pipelines to convert the data to the format that they want. Okay, and you could have your data scientists do some processing, to transform data and then put it back in and make it available to other people who then could discover your processed data through the catalog. That's the dream. That's the vision of this. At the end of the day, it comes down to humans. Like how good are your engineers and your data scientists going to be about keeping track of the provenance of the data that they're writing out, providing documentation for other people to use it, right? It's hit or miss. And again, the advantage of this is like you could have your some part of your application, some microservice, writing about S3 files into S3, and then something that's running like a Presto or Trino could then just run SQL queries and parse it without having to first go and ingest it and sort it in the whole pipeline. You just plop it in S3 and then let everyone else consume it. So again, there's pros and cons. I'm not saying one is better than another. It's certainly a lot faster if I just dump S3 files or a bunch of files in S3, don't define a schema, then worry about how to keep the schema in sync between different versions of the files later on. That'll be much faster than having to define the table ahead of time and do much work to clean things up to put it in.
Yeah. Right. I mean, for you to keep in mind, it's really important that sometimes data lakes are advertised as the solution to managing large data sets. That will solve everything. That's it's always the same thing in the database industrial world. Yeah, there are buzzwords that I talked about that many times before. Just be careful if someone claims, "Hey, data lakes are the solution to everything." No, they're not. It's just a distributed file system plus catalog. Yeah, you will pay the price at query time, so be careful with that.
All right, so now we've been sort of dancing around. I mentioned this a little bit already. The data that we could be storing in a data lake or in an OLAP system, it doesn't have to always be just text files or CSVs. So traditionally, most data systems have their own on-disk binary format for the pages, right? Think of like when you're in BusTub, it wrote pages out to disk. There's a little .db file. We should probably call it .busTub. We should fix that. But there's a bunch of .db files, and that's a proprietary format that only the database server knows how to maintain. Actually, my favorite story about SQLite is there's an internal file format that SQLite writes out the disk, and he used to have it. The creator of SQLite used to have it be .SQLite, but then he started getting phone calls from people because a bunch of different like applications were using SQLite, for like think of like Photoshop or something like that, like desktop applications, and would write out .SQLite files, and then the system would, the application would crash. Nothing to do with SQLite, like the application was buggy, it would crash, and then the user would then look at the local file and see a bunch of .SQLite things and assume that was the problem. So then they found his phone number and would call him and complain about SQLite, right? He's like, I don't know what you're talking about. So in the code, you can see it where the temporary file is dot and then SQLite spelled backwards, right? ET, whatever, like IL. And that prevented people from calling him because they don't know what it is. Anyway, but that's like, that's like the SQLite proprietary format. Postgres has its own proprietary formats. Like everyone has their own thing. So the problem is now, if I want to share data between these different systems, I got to take it out from the SQLite format or the DuckDB internal format and then convert it through some process into another internal format so that some other data system can consume this, right? Or alternatively, I just write it out as a bunch of CSV or JSON files or XML files, but that's going to be slow because you're taking binary data, converting it to text, and then have to convert it back into binary data. So they're not really new anymore. It's over 10 years now, but there's a bunch of these open source binary file formats that these systems can natively consume and generate so that I can write out a bunch of these files from my one system, write them in S3, and then have some other system know how to consume them and run queries on them. So the most famous one is probably Apache Parquet, and this came out of Twitter and Cloudera. Orc is one that came out of Facebook and Hive. They're essentially the same thing, but think of like it's a columnar format that is compression. It does zone maps, a bunch of other things, right? And the idea is that they have this standardized format, then they have a bunch of different client libraries written in different languages, like Rust or Java or C++, that you can then use to consume and get the data out of these things and write them. Carbon data came out of Huawei. This might not a scam, but it doesn't work, and I don't think anybody uses it. Like you try to run the code, it doesn't work. So all right, that just means the open source version might be different from what they have internally, but the open source version doesn't work. Iceberg came out of Netflix. This is Parquet plus.
Yeah, we don't have to go into all of these formats, but the main idea is really, and that's important, not only for distributed systems, but for all kinds of database systems. Whenever you read and write data, there's an opportunity to read or write data in a format that can be understood by a different system. Yeah, so if you write it out, you might use not some proprietary format you came up with, but you could write it out in a format that other systems could then read. Yeah, so that's a natural exchange point whenever you read or write data to a storage medium or to a network. And that's very important in distributed systems. You assume you want to do an analysis with one type of system, and maybe you do heavy lifting, query processing on large data sets, terabytes of data, and then you compute a certain query result that is then to be processed with a Jupyter notebook, for instance, or whatever, another query engine. Yeah? And then the question is, how do you exchange the data? So the results you processed with the first engine, how are they exchanged to the other system? And of course, you could do something like JSON, XML, stuff like that. That has the disadvantage that you have to parse the data. It's textual data. It's heavyweight. And it may be okay for smaller data sets, but if you want to exchange larger data sets, you have to have something more efficient. And that is the story he's telling, basically. So today, it's not so much... it's often... previously, data analysis was done in one system. Actually, it was only a database system. You analyzed all your data in a database system. Now it's more an open world assumption that, okay, you do part of the analysis in one system, then another part in another system, and therefore you have to have formats that allow you to efficiently exchange the data, but then also efficiently write and read the data, such that you can switch over from one engine to another without losing too much performance. And that is what all of these formats are about.
Some additional files for ingesting data, right? Because these file formats are write once, write once, read many, meaning like once I create the Parquet file, I can't make incremental updates to it, right? Because again, think of like S3, I can't make fine-grained changes to an S3 bucket. It's either put it or get it or delete it. So I'd want to generate this one of these Parquet files and just write it all out. And if I need to make incremental updates, you use something like Iceberg to keep track of these things and then merge it later on. HDF5 is an older format from the 90s. This is primarily used in like HPC or scientific workloads. Like think of like the Hadron Collider. You would smash them, whatever atoms, and then it would produce a bunch of these measurements, and it'd be in HDF5. And Apache Arrow is a newer one that came out of Pandas and Dremio, and this is for in-memory representation of columnar data. And the idea here, which is kind of cool, is that you could store your data in memory in the Arrow format, and either do fast transfers over the network to send it to another node, or potentially have another process running on the same box as you peek into your memory and know how to consume the Arrow data directly. Again, without having to serialize it or copy it out.
It's the same idea. Yeah? Whether you represent it in memory and have multiple processes reading from it, or one is writing and the other is reading from it. If it's a memory across machines, across systems, it's the same idea. It's a point of data exchange, and they have a common format. Important here also, Apache Parquet is basically the PAX layout, partition across layout we talked about earlier. And all of these other formats, also Apache Arrow, as far as I know, also a PAX layout. So basically, horizontal partitioning first. Within a horizontal partition, you do column layout, and the columns are compressed. That's the most widely used layout. We talked about that when we talked about storage layouts, data layouts. Compressed columns is the best thing typically you can do. It works in most of the cases super well.
So Parquet and Orc, Parquet is probably the most common one out of all of these. And then Orc is probably the second most common one. And again, all these different OLAP systems will have their own connectors or know how to parse these things and consume them. The other things that we've talked about so far is how to break up the system even further. We talked about system catalogs. H catalog is the most common one that came out of Hive. Again, I think it's the metadata about the data, like where the data is located, what format it's in, potentially some additional statistics. But Google and Amazon and Microsoft have their own catalog services. To run the nodes, Kubernetes is the hottest thing now. It's a de facto standard, so everyone uses that. Then the cloud guys have their own stuff. And then we didn't really talk about query optimizers as a service, but in some systems, since building query optimizers is super hard, instead of everybody replicating this process over and over again, I try to pull out and extract out the query optimizer, make it be its own standalone thing, so I could build a new database system that could reuse one of these query optimizers to parse the SQL, generate a query plan, and then I just have an engine that can actually run that query plan itself. So the most famous one is Calcite that came out of LucidDB. LucidDB was a startup that failed, but then they pulled out Calcite, and that became the optimizer as a service. Orca came out of Greenplum. Calcite's more common, but Orca is another alternative. Again, so in theory now, you can kind of build your own OLAP system by like reusing this piece and this piece and this piece and kind of like munge it all together in a cloud service without having to write everything from scratch over and over again, which is kind of cool. All right, so just to finish up, I think there's a lot more activity and a lot more money sloshing around in the OLAP market than there is in the OLTP market. And I think the cloud has made this so much easier. So there's a lot of different vendors. They're all hiring. And there's a lot of interesting problems still in this space. But of course now, you have a lot of money, you got a lot of data, and it makes things a lot harder. So go get jobs and help these guys out. All right. So.
Okay. Yeah, that's true. There are many of these vendors in the OLAP market that also in our offices in Germany that frequently approach us. Some of my former students actually work in Berlin for a big vendor. Anyway, so that's it for today. I was just one thing I would like to try, because that was a reaction video. But in theory, I was wondering, what if I open the stream of this video that I'm just sending out? So I could do a reaction video on my own reaction video, right? I mean, what would happen? I'm not so sure. I just would like to give that a try and see if that's even possible technically. Anyway, so that's it.
Would potentially have to have either file formats that the systems can.
Done in one system. Actually, it was only a database system. You analyzed all your data in a database system. Now it's more an open world assumption that, okay, you do part of the analysis in one system, then another part in another system, and therefore you have to have formats that allow you to efficiently exchange the data, but then also efficiently actually works. I could do
such that you can switch over from one engine.
What if I go to the end of the stream? Do I get a kind of loop?
Actually, it was only a database system. You analyzed all your data in a database system. Now it's more an open world assumption that, okay, you do part of
So it's reaction on reaction on reactions and infinite recursion.
system, and therefore you have to have formats that allow you to efficiently exchange the data, but then also
Yeah, it would actually work.
works.
I could do
such that you can switch over from one.
do my own reaction within the same
If I go to the end
reaction.
of the stream,
Do I get a kind of loop?
Actually, it was only a database system.
Yeah, anyway, so that's silly, but we have to be silly sometimes. So, how do I stop that?
Reaction on reaction on reactions and infinite recursion.
Anyway, so that's it for today's lecture. So in the lab on Friday, we will take a look at the different joint processing scenarios. We already have an assignment on that. We will upload it today. So the lab will be on Discord. Again, we have this energy saving week. So on Discord on Friday, next week, Wednesday, in the lecture hall. Thank God again. See you then. Bye-bye.